Yeah, so I do record my lectures and post the recordings on YouTube. Okay, but the reason why I do that is not to encourage people and say, oh, this is the same thing as an online class. No, it's for you guys to review the material. Okay, so if you are taking notes, one thing you can do is to note the time when I start to talk about a certain topic. So that way, when you go to the recording, you can hopefully quickly, you'll kind of fast forward to the time mark, and you don't have to watch the entire thing or scan the entire thing for that 2 minutes that you just want to listen again. Okay. But this also means that the way you take notes may be a little bit different from your other classes. There's no need to frantically write down everything that I talk about or on the screen because my voice is recorded, as is everything that you see on these screens. So you can focus on the concepts, focus on what you are thinking about. This reminds me of this topic in that class. Jot it down, okay? Because that is the most important part of what your note should reflect. And I'm just going to double check, make sure that the streaming is on. Yep, it is. All right. Any questions before we get started? Questions? All right. So if you're like me, sometimes you have a dry throat, because of air conditioning and whatnot. Just be very careful. Don't spill water on the computer. Be it yours or the school's. And I know some of the tablets are rated splash proof, so maybe those are not a big concern. If anyone wants me to wear a mask, that's fine with me. I don't have a problem wearing my mask too. Just let me know. You can send me an email if you don't want to raise your hand. Just let me know somehow. But otherwise, it's easier for me to. I don't project my voice well like some of the other professors. So without a mask, it's a little bit easier for me to talk in the class. All right, so let me switch back to the Canvas presence. And we're going to start with the syllabus. So all of you should be able to log into Canvas already. If you have a mobile device, like a tablet, or if you have your own laptop computer, you can just kind of go to the web page where I'm talking about things. So that way you don't have to look at the screens as much. And so when I scroll, you won't get motion sickness as much either. So it's up to you guys to decide how you want to look at the material. But most of the material that I have, unless it is a demonstration, if it's a content type of material, it's already on Canvas. And because I'm kind of old, this is what I need to look at things that are close. Yes, go ahead.
How do you turn on these computers?
So they have a little computer, which is at the back, lower of the back of the monitor.
I see.
And I'm not sure where the power button is located.
It's on the top right side of the actual computer back there.
Okay, yeah, on the right hand side.
It's like a little slit, kind of looks like a drive.
Yeah.
On the right edge, top of the right edge.
And then on the monitor, yeah, you got it.
Yep, there you go. Yep, so you got it? All right. So the first part is really just me talking about the syllabus. So it's probably not super duper important for you guys to sign in to use the computer resources. So when we get to the actual class content, that's when it becomes kind of more important. All right, so let me get to the syllabus. And I'm gonna just change the font size a little bit so it's easier to read in class. So I'm just going to go through every single one of these items. The section 1 is just something that you should know already. This is CISP310, not 300. Somehow the counselor told people, this is the class to start with. And that is not the case in computer science. Okay, this is definitely not the first class people should be taking. Course description, that's catalog stuff. We have 54 lecture hours and 54 lab hours. That makes this a 4-unit class because the 54 lecture hours makes up 3 units, and then the 54 lab hours makes up the additional unit. So it's a 4-unit class. Well, I suppose I might as well do it now. What a unit means is a little bit interesting because in addition to class time, people are supposed to spend twice as much offline. Okay, so in this particular case, we spend 80 times 2, which is 160 minutes per week, in lecture. So that means, 320 minutes is the expected amount of time that people should spend outside of lecture, outside of lab, to study the material, to preview the material, to kind of review your notes, to reorganize your notes in order to succeed in this class. I just want to kind of mention this, so that you can budget your time accordingly. All right, next is prerequisite, which is also a very important topic. Prerequisite is required. The division and the school, the college, requires me to enforce prerequisites. Now, does that mean that, but I have 20 years of programming in C++ under my belt. Do I still have to take CISP360? The answer is no. Okay, you can actually go through what we call a prerequisite challenge petition. So that way, if you have taken this class from some other colleges before, hey, no problem. Okay, just include your transcript along with the petition, and somebody other than myself would evaluate your petition. And if everything checks out, hey, no problem. You can stay in this class. Okay. Student learning outcome is too early to really describe this because that's basically what you're supposed to walk away with. Okay. So when you are done with this class, you should be able to write simple assembly language program segments. And so on. Okay, so I'm not going to go through the list here because that's exactly what I'm supposed to teach. If you already understand all of this stuff here, you really don't need this class. So I'm going to move on to class information. This is the section number of this class. We meet, you're here already, so I don't need to mention when the class starts. And we do have a lab right after. I'm inclining to have lab activities today. It's not going to be very extensive or difficult. It's just kind of following a few steps to get things done. All right. But the schedule is, has already scheduled you during this block of time. And that's what I'm going to assume is you guys will be available for the entire lab period. Even though some of the labs are really short, you may be done in half an hour. Okay, well, if you're done, you don't need to be here. You don't have to stay here. You can just kind of, go wherever you want. This is a full semester class. This is the official start and the end date of the semester. Obviously, the end date of the 15th of December is also including the finals week. Now, because this is an in-person class, we do have a designated final exam time as per the campus exam schedule. So you can just do a Google search, American River College final exam schedule, and that should get you to the right page. Like the first one should be the right link. All right, so I'm not deviating from the scheduled final exam time. So if you want to kind of block off your schedule to make sure that you have that time blocked, just go ahead and search for that. The drop date is November 15th. All right, so about me, I'm Tech. My email is that, okay, it's hard to just kind of spell out the letters, but it's AUYEUNT. The G is not there because the district decides to keep only the first 6 letters of the last name and then plus the, first 6 of the last name plus the first initial. As you can probably imagine, if somebody is a Smith, that can be a little bit problematic. My phone is 484-8250. I am in the office, now that I'm in person. So, if you call me during my office hour, I will be there. So I can answer the call. But most of the time, otherwise, I'm not going to be able to answer the phone. So you can leave a message. Your message will turn into a MP3 file, and then they just send me an email with that as an attachment. So it will still be able to get to me using the phone, but email will be kind of my first choice. You can also use Canvas, messaging, that should get to me as well. Office hours. For Monday, Wednesday, it's right before this class. So you guys are kind of lucky because you're right, it's the first class of my Mondays and Wednesdays. So anytime, 1 hour before the class, if you want to be here earlier and just kind of thought, okay, I might need more time to talk to you about something, I'm typically here before 9:30. So if you want to talk to me before 9:30, just let me know ahead of time so I can tell you for sure that I'll be here before 9:30. But because my son, who comes to school with me, he has a class starting at 7:30. So until he learns how to drive, I'll be here like way earlier than I need to. Tuesday, Thursdays, I'll be here from 8 to 9. And then on Fridays, I'll be here from 9 to 10. My office is STEM 316. Do you guys know where to find offices? Sort of? Okay. So if you walk out of this door, walk down the hallway, there is kind of like a enclosure, with a lot of rooms inside the enclosure. That's where the faculty offices are located. My office is 316, which is all the way to the end on the right-hand side. So you see a room with a refrigerator, that's the workroom, but my office is immediately to the right-hand side of that. Okay. All right. Any questions so far about the syllabus? No questions? All right. I'm actually savoring being able to see faces instead of tiles with somebody's, static picture of something else, right? All right, so presentation delivery method, you have reading material. So I will get to the reading material. Everything, all the reading material is already in Canvas. So all those links, okay, you just kind of click on those links and read those links in order, in sequence, and you'll be fine. Okay, they're already pre-ordered. So if you just kind of go through those links, one by one from top to bottom, that's kind of all the reading material. There's no textbook to purchase. Now they're, really trying to promote OER. Do you guys know what is OER? Okay, it's Open Education Resource, which basically translates to free material for classes. I've been doing it for 22 years, but now they're starting to give people stipend, to develop your OER material. So I'm just wondering, can they back pay all the time that I have spent to create my notes for the past 22 years? So there's video clips, not really a whole lot, but the lectures are recorded. The lectures in this case is in person, face to face. And then the lab are basically interactive activity in Canvas. All right, moving on to section 6, regular effective contact and communication policy. To stay in touch with me, you can utilize my office hours. You can email me. You can also message me using the Canvas mechanism. So, all of these are ways to get in touch with me. Expectation of time frame at the turnaround time of no more than 24 hours to message sent between Monday midnight and Friday midnight, excluding college holidays. Otherwise, a turnaround time of no more than 48 hours during a semester. So I got to expand on this section a little bit because I am used to online teaching because of the pandemic. So during the pandemic, I have actual synchronous office hours, but nobody ever used it. And then throughout the day, I get messages popping up here, messages popping up there, and so on. So in this case, because I'm in focus, in person, you guys are in person as well. So try to utilize the office hour. After this class, I have another class at 3, which means, if you want to, you can just let me know, okay? I got something to talk to you about. and then we can have that discussion after class as well. So try to utilize that time. Now, some people may not need to use the entire lab time. So if you see me just idling, got nothing else to do, we can go ahead and also have a discussion of whatever you want to talk about. We might have to take the discussion outside so as not to disturb the rest of the class. But so try to use the in-person time because that's one of the things that we are trying to do is to, hey, we are all in person here. So if you want to communicate, talk to me, talk to me. Don't, I mean, I will still respond to email, okay? But the preferred way is to do it in person. All right, moving on. For in-person and synchronous class, office hours are scheduled at the discretion of the instructor. Questions may be answered or addressed between office hours. So that means, between my office hour today and the office hour tomorrow, if I have time, I go through all my email messages and I can still answer those email messages. Okay, but I cannot guarantee like within half an hour or within 15 minutes because I think that's what a lot of people, including myself, have start to expect, right? You go online to shop for something, and then there's a little box, the chat bot, and go like, okay, if you have any questions, we are right here to answer your questions. So being in person is a little bit different. It is best to utilize the office hours of the instructor. So that's what I said earlier. Additional meeting times can be scheduled at the discretion of the instructor. As long as I can make it, I typically would just kind of like, oh, well, since I'm here, might as well. So go ahead and schedule the time, when I'm around. Any questions so far? All right. Yeah, it's pretty hard not to meet the requirements of regular effective contact when a class is in person. To do that, I basically have to kind of put a blind on my glasses so that when you guys raise your hand and scream, I got a question, I have to choose to ignore that. Okay, I'm just joking, but half joking, because I have heard some experiences of online teaching where students have questions and the instructor there's no way to get to the instructor. I see some noddings, because it can happen, but it's much harder to happen in an in-person class because I actually have to put in a lot of effort to ignore questions and people raising their hands. I love questions, by the way. Okay, accommodations. This is about disabilities and whatnot. So I'm just going to tell all of you where to find the DSPNS service, where to find them. They are at the north side of the now called Welcome and Student Services. I cannot remember the full name, but there's a link to the homepage and there's also a link to the email. So anyone who think you might need their services, you can contact the DSPNS department. All right, moving on, unless you guys have any questions. Okay, so the conduct section used to be really long in my syllabi. Now it is just a reference to the college, the expectation of behavior and contact, which is a link to the college's own webpage. The instructor's policy is to be consistent with the expectations from the Office of Student Conduct. The instructor will report all cases of violations. The minimum consequence of a violation is a score of 0 assigned to the assignment that is in violation in the case of academic dishonesty, otherwise known as cheating. Exactly. So in the case, we don't have any plagiarism, to worry about in this class because we're going to write code in a language that is not really used outside of this classroom. So I think the chances of plagiarism is almost 0. Okay, but there are other ways of other forms of academic dishonesty. In the case of violations that are not of the nature of academic dishonesty, such as bullying, the involved people may be removed from one or more class meetings. The Office of Student Conduct may incur additional consequences. So this becomes a somewhat important topic because just last semester, spring 2022, I caught two of my students cheating in a final exam. And since I put the policy in my syllabus, I did not really have much of a choice but to report it. Um, so that's kind of important because I think one person ended up not being able to transfer, and I'm not sure about what the other consequences to the other person. So it's really kind of important. All right, moving on. Absences and attendance. So refer to the attendance on the college's webpage on college and academic regulations. Specifically, the district has a requirement for attendance. So for the first, so I did not make up these rules, okay? But the district has the rule of if anyone misses any one of the first three classes, that's enough, reason to be dropped. And then for the rest of the semester, 6% is the threshold of what is considered excessive. So once you do all the calculations, missing the second class of a class like this one, where we meet twice a week, is already 6 point something percent. So that means the second absence is already quote unquote excessive. Now the college did not define any policy of what absences can be excused. That was the case in high school. Okay, so in high school, I think Title II or Title IV, it's actually a government regulation. Actually, outlines what should be excused and what and so there's an actual policy. But in this college, because we are working under Title V for higher ed, interestingly, there's no such policy. They do not define what has to be excused. So instead of me defining what should be excused and have fuzzy wording and whatnot, I am using a different policy. And let me see if I can find that. There we go. So I'm just skipping all the way to what matters, which is section 9.5. So what is tax policy? So right here, 3 times. Okay, so 3 absences. You can have up to 3 absences before being considered excessive. So I think that's fairly generous because the second one, in theory, is already a quote unquote excessive. So this way, the fourth one is excessive. Are we understanding this okay? All right, excellent. Now, the idea of why do we kind of care about absences and why attendance is important? There are several reasons. One is in order for the college to collect money from the state, you're supposed to be here. Okay, that's one of the requirements. But the second one is more important because from your perspective as a student, I think, because I was once a student, I think it is important to attend classes because, depending on the person, I absorb, I would say, 90% of the content when I'm actually in the classroom during a lecture. Now, some other people may say, yeah, but I'm about 60% or 45%. Different people learn differently. I can tell you stories about that because I talked to someone about this, and it turned out that hey, it can be very different. But nonetheless, missing a class, having the lecture and the interaction can be detrimental. So that's why it's important to have attendance as much as possible. Okay, so grading is a long section because in this class, I don't bother to test for knowledge and your ability to recall. And you might ask, but why? Because all the exams are open book and open notes. I mean, in this classroom, I have not decided yet to make it open computer. You can Google, okay? As long as you're not interacting with someone or collaborating with someone, for the exam, I don't really care, okay? Because when you work as a software engineer or as a developer, Do you think your employer, like Valve, is going to say, you know, Tech, if when you're working, we're going to shut down your internet access. You cannot have access to online material whatsoever. You have to remember all the API, the entire syntax of every programming language that you're supposed to use at work in your head. We're not doing surgery, are we? I can understand why surgeons may have that requirement because you don't want a surgeon to go like, nurse, iPad. Can you get me to the Wikipedia page on that particular artery? I'm not sure what the name is, just that one over there. That might not be good, right? You don't want to get into an ER or a surgery where your surgeon is relying on an iPad to find out which artery to clip, to so it won't bleed excessively, or the guy who's in charge of your medication, to kind of have to look up everything to find out, the side effects of everything, right? So, but we are not in that boat, okay? So I think, it is not important that you have to keep everything in your head. So what am I going to test? What I'm going to test would be your ability to analyze and to think, as well as your ability to problem solve. Okay? So let me give you an analogy, okay? Because I cannot use the class content because we have not gone through the class content yet. So think about a car not starting, okay? So I'm not going to ask you guys and go like, okay, tell me about the battery capacity of this car. You can just look it up. I mean, just open the hood, look it up, and go like, oh, okay, this one has 550 cold cranking amps, okay? It doesn't make any it doesn't make any sense to ask you, for something like that. Or what is the VIN of this vehicle? You just have to go to the windshield, where the VIN is displayed, and just tell me what the VIN is. So instead, I'm going to give you a car that doesn't start, and then the first part is you kind of have to tell me what components are necessary in order for the car to even crank, okay, to even hear the starter, motor to crank the engine. So you guys might think, oh, okay, so we'll start with the battery, okay, because that's where the energy is coming from. And then you have the terminal on the battery itself, and then you have the wire that connects to the starter, the switch, and then the fuse, and then the starter motor. So you have to name the components. So now if the car is not starting, it's most likely one of those things is not working the way it's supposed to. Okay? And then I would say, okay, now help me fix this problem. Okay? So what do you do? Well, assuming this is a shop class, okay, where you actually have access to the car, the first thing you're going to do is to test the battery, make sure it's good. Okay, everything checks out. Then you check the terminal, make sure it's not oxidized, it has good contact. Checks out, not a problem. Then you check the cable, then you check the fuse, you check the switch. If they all check out, then what do? Well, if the engine is cranking but it's not starting, now you have an entire different system to think about, right? The fuel delivery, the spark, okay, assuming it's not a diesel engine. So I want to see how you guys problem solve, and also how you solve a problem. How do you fix the car that wouldn't start? So that's kind of the focus of all the exams of this class. Will be focusing on those particular items. Now, does that mean knowledge is not important at all? That you guys think, oh, I don't need to remember the definitions. I don't need to understand all the symbols because I can look it up. Would that be an effective way to get through this class? Probably not, because the familiarity of the symbols and the definitions is what changes how much time it takes for you to problem solve. Because if the symbols are all foreign, at the time of the exam, then that person is going to be spending a lot of time just to look up the definitions, just to look up what the symbol is representing, and so on. So you still want to have you still want to basically have a good understanding of the symbols and the definitions. It's just that the application, of those definitions, of how to solve a problem, that is what you need to do during the exam. All right. So next one is performance, which is the dimension that quantifies the familiarity and efficiency of performing critical thinking and problem solving. In other words, I have had students in the past, probably students in the future, that who had and will talk to me about, but I can't solve this problem as long as I get a little bit more time. Okay, so now the question is, why is that important? How much time it takes to solve a problem, and not just can a person solve the problem, but it is more about, well, but can you solve the problem within a certain amount of time? So does anyone want to kind of chime in to let me know why you think this is important? Or if you disagree, that's fine too. You can say, I really don't think it's, okay, you go ahead and then Rayshon is next. Yeah.
Working deadlines.
Working deadlines.
If you have a job, you have to get your job done in time.
Wow, that's like a foreign concept, right? I mean, if I go work for Intel, which is infamous for giving people an excessive amount of work, they know that you have 40 work hours, but they will give you 80 hours of work worth of work per week. Okay? So in those situations, what if somebody is to say, but boss, I can do this, okay? Give me another like 4x amount of time, I can still get it done. What do you think is going to happen? I can see people turning their heads because in a private organization, it's all about I pay you this much money, and how much productivity am I going to observe? Okay, so that balance has to be there. Okay, and then some people may translate this to a academic situation, go like, but that's work stuff, right? This is a school, I'm supposed to be learning. Why is that also important?
Well, I was gonna say deadline, so,
Yeah.
but he's already said it.
Yep. So I will have, so exams are timed. In other words, once the exam is open, it's going to be in person. Okay, we only have this classroom for so long before the next class has to come in. And even if there's no next class, I cannot schedule outside of the lab and the lecture time of this class because other people may have other classes. I cannot just say, I'm going to extend the time of this exam. So for those of you who can stay, you get the extra time. But if you have another class starting right after this one, I am sorry, you're not going to be able to use the extra time. I cannot do that. Okay, that would not be good. So performance, can be a part of it. Now, does that mean I'm going to curve the grade? So the person who can get it first is the only person who's going to get an A, and I'm just going to, look at how much time people take to give them the letter grade? No. If the entire class can meet that standard, can finish the entire exam, get everything right by the end of the period, the entire class can get a grade of A. Okay, it is not relative to each other. Okay, your grade is relative to what I think people should be able to do, but it is not relative to other students in this class. Now, is it good or bad? Well, it's both, because now you're being compared to my standard, so I have to make my standard really known and make it realistic too. Okay, so that's on me. But it's good in a way that you're not in. I'm trying to think of the right words. Just give me a moment here. You're not in unhealthy competition with your peers. So you don't have to worry, hey, if I help you understand that concept and you end up with a better score than I do, then you might end up getting an A and bump me down to a B. That will not happen. Okay. Unfortunately, some of you will probably understand that once you move on to a UC, especially some of the more competitive UCs, that is actually the case. It's all relative. The professor will curve the class so that only a certain percentage of students can get a good grade. Okay, which I think is sometimes, that's like, it makes people really cutthroat, and then people won't help each other. And that's probably not the best way to to assign letter grades. All right. So meanings of 0 to 4. If you just read the title, it doesn't make any sense, right? This is a programming class. You guys should know what is a 0 and what is a 4. So the question is, what does it mean when someone gets a 0 for a portion of an answer? Okay, because it's all rubric based. So for one question, there can be multiple parts to an answer, and then even for each part of the answer, I might break it up into several parts. So what does it mean when somebody gets a 0 out of 4 for that one chunk, of whatever criteria or criterion that I'm using for grading? So a 0 is probably really easy to understand. Either no work is turned in, though nothing is submitted. The submitted work shows no evidence of the ability to analyze and think critically, the ability to synthesize or problem solve, unless otherwise specified. Code that does not compile or assemble, which applies to this class, will also get a 0. Examples of answers is, for that I have to get back to the example here. So I made an example of what type of answer would get what grade based on the question of using algebra, show all steps and explain each step to find the solution of x squared minus 1 equals to 0. I'm hoping everybody in this class has some idea of how to solve that problem, okay? So that's the question. If the answer is just x equals to 1 or x equals to minus 1, that answer, I'll give a 0 to that particular answer. Why? But tech, it's right, okay? You substitute 1 into x, x squared minus 1 is indeed 0. If you substitute negative 1 to x squared is negative 1, the whole thing squared, that's 1. 1 minus 1 is also 0. Why am I getting a 0? Yeah, go ahead.
Because you're not demonstrating that you understand how to get that.
Exactly. So even though that person in the head may understand, oh, I know exactly how to do it, but there's no demonstration. I'm not a Vulcan. I cannot mind meld and go like, yeah, I can see that you actually understand the material. I cannot do that, okay? So unless I see evidence of the problem solving, step-by-step problem solving, I have to go like, but it's not demonstrating anything, okay? Because the question is not asking about the right answer, it's about how you derive the answer. You have to demonstrate to me that you know how to solve that problem step by step. All right, so I'm going to skip all the way to 4.4 over 4. Like, okay, so tech, using your standard, what kind of answer is going to get a perfect score in this case? So in that context, I'm going to say, all right, so okay, I have to collect my thoughts here. So this is one part of the answer. You basically go like x plus 1 times x minus 1 becomes x squared minus 1. At this point, this is one way to get the right answer, is to use the quadratic equation solution. So you can quote, if this is discussed in class, you can use it, okay? It's a tool that you can use. So you have to specify, this thing here can be expressed in the form of ax squared plus bx plus c equals to 0. But in that case, a is 1, b is 0, and c is negative 1. And then, if I have already talked about the solution, like in this form in class, you can use it as well. But you have to tell me that you are using that tool, okay? And then you say substituting a equals to 1, b equals to 0, and c equals to negative 1. Then you get x equals to 1 or negative 1. So that is showing steps. Alternatively, if you use algebra like the first part here, that would also be acceptable, because now you can say if one side of the multiplication is 0, the product is going to be a 0. So how do we make x plus 1 a 0? Solve for that, right? X plus 1 equals to 0 using algebra. Now you can say, oh, x is negative 1. Good. What about the other part of the product, x minus 1? How do you make x minus 1 0? Once again, use algebra. And once you solve that equation in algebra, you get x equals to 1. So that would also be acceptable. But you have to show me how you solve it. So this will suck for people who just kind of go online, go to Mathematica, and just say, okay, solve this for me. Okay, this is the answer. I'm just going to copy the answer onto my answer sheet. That's not going to work, right? So because you have to show steps. So B is basically kind of like an A, except someone made a minor mistake. So in this case, the minor mistake is when substituting, that person said, A equals 1, B equals to 0, and C equals to 1, which is not true because C is supposed to be -1. So this is definitely a clerical mistake because there's a -1 here, and somehow that person thought C is supposed to be 1. So I would understand it as a clerical mistake, which is not a conceptual mistake. But nonetheless, it is still a mistake, and so that will bump the grade from an A to a B. And you can read the rest, what is a D and what is a C. So basically, it is just a level thing, like to which level am I getting evidence that that person understands the concepts and be able to apply the concepts, and what kind of mistake or omission am I looking at. Are we good so far? All right. Now, because I grade all the exams in this particular manner, so that means, at the end of the semester, if X is the score that you're getting, the ratio of your score over the total amount that is possible, then a D, an F, let's start with an F. An F is anyone who gets less than 12.5%. I don't think anyone's going to argue that if a person gets less than 12.5% of all the possible points, probably should get an F. Okay? A D is somewhere between 12.5% and 37.5%. That's a D. And I'm hoping nobody in this class is thinking in this way, but there is always a possibility because some people may just be thinking, I just need to know what is the percentage to get a C, because that's what I need to get out of this class and move on to the transfer. So that's a 37.5%. Does that make this class easier? Nope. Because why? Because there are no questions asking about just knowledge. Okay, for all of your other classes, there are probably a lot of multiple choice questions where it's just asking you about the knowledge. Okay, I don't really care about that because I would assume that you would always have access to it, and you should probably understand and have a good base, good understanding of the knowledge part already. A B is 62.5% to 87.5%, and then an A is anything that is at least 87.5%. So are we good with how I convert your score percentage to letter grade at the end of the semester? Are we good? All right. So there are 1, 2, 3, 4. There are 4 categories of assessments: homework assignments and lab activities. So that is making up 20% of your grade, of the score at the end of the semester. Okay, not a whole lot. Okay, but it's not 0 either. Okay, so it gives you guys a little bit of incentive to work on the homework assignments and also the lab activities. But I would point out, okay, that some people look at the lab activities and look at that 20% and go like, I just need that number. I need that 20%. So what they do, because in the labs, I typically would make the labs so that you can retry as many times as you need within the time limit, which is basically the entire lab period. And some of those questions are multiple choice. And I also set it up so that it would give you the total score. You can just basically answer a few questions, click submit, it will give you the total score. If it's not 100%, you can try again, okay? So the idea behind this particular decision is so that people would not feel disappointed, okay? I didn't get all of it, okay? But that's okay, as long as you go in and try to find out why you did not get all the points, learn from that experience, and it's all good. But some people look at this and go like, oh, I see a loophole here, okay? Because what I do is I'm just going to go to answer the first question. I'm just going to sequentially go through all the options if it's multiple choice until I get the perfect score for the first question. Then I move on to the second question, do the same thing. So eventually I'll be able to figure out every correct answer to all of those questions. And then I'm going to get a full score for the lab. So from my perspective, how do you think I can find out that's how some people work? When someone has 97 attempts, you can kind of guess like, what? So I know that some people work on the labs like that, which defeats the whole purpose of the lab activities. Okay, because the lab activities were supposed to reinforce what I teach during the lecture. So if it's not a full score, you find out why it's not a full score. And we are in person now. You can actually ask me to come over to ask me why am I not getting a full score? Okay, which brings up another thing that frustrates a lot of people to no end, because I typically answer a question with another question. Exactly. So I never give people straight answers. And why do you think I choose to do it that way? Because let me tell you this thing, because most of you do not understand. From the perspective of a professor or instructor or teacher, it is actually easier to give you a direct answer so that you don't come back and ask me again. So why would I formulate another question to answer a question?
Get you to think critically.
Hmm?
To get you to think critically.
Exactly, because I want you to think, but I'll give you a direction, right? So I'm just going to point to a certain direction and go like, try that direction, okay? Because this way, when you figure out the answer, it is actually going to be the knowledge, okay? And the skill is yours. If I just flat out give you the answer to the question, can you imagine how long that's going to stay in your head? Probably just about when you walk out of this classroom. Because if I were the person, taking the exam and somebody just gave me the answer, that's how long my mind will retain that particular piece of knowledge. But if you work on it, it's going to stay there for a while. And do you know why? From the perspective of brain science and neuroscience, why is that the case? Because when you work out the answer, you're establishing pathways to that answer, and multiple pathways at that too. So that means you have more ways to recall the knowledge, you have more ways to recall the skill, you have more ways to recall the technique the next time you encounter something like that. That is why, if you work on it, you really try to work on the problem, it might be frustrating for you because you might be spending 10 minutes and you go like, I don't think I'm going anywhere. But you are actually going somewhere because you have at least figured out what does not work. Okay? And most people think, why would I want to know what does not work? Because that's also part of what you're supposed to learn. All right? It is important that you guys try as much as you can, to try to get to the solution by yourselves. Okay, so with that said, the first exam, which is usually about 1/3 through the semester, is another 20%. The second exam is another 20%, and then the final exam all by itself is 40%. And someone is already clicking in the head and going, I need 37.5% to get a C out of this class, and the final exam by itself is 40%. I'm just going to take the final exam and ace it, and then I'll be fine. I'll be good. I'll be passing this class with a letter grade of C, and I can transfer. This is not a challenge, okay? So don't look at this as a challenge and go like, okay, since tech is challenging me, I'm just going to try to do it, okay? It's not because of that reason, okay? I'm assigning 40% to the final exam, 40% because that's the integration of everything that you learn in the semester, okay? So that's why it is 40% is more important. All right, any questions up to this point? No questions? All right, Complaints? Disagreements? Nope. Okay, well, I'm actually quite open to disagreements too. I'm not going to show you what I got, when I taught online, okay? But some of those conversations they're interesting, okay? Just different people having a different perspective. Um, I can tell you some of that, okay? Some people complain that I do not teach to the exam. In other words, I don't reuse exam questions ever. Well, at least I try not to, but occasionally I might just accidentally reuse the same question because I just kind of thought of the same way of asking that question. So I have gotten people, I wouldn't say complaining to me, but indicating that I should be teaching to the exams. In other words, teach us every technique that will help us, so that we can just regurgitate, we can just repeat the process in the final exam, and we'll be good. And I do not do that, okay? And why do you think I do not do that? Why do you think I always make the exams a little bit challenging? It's something that you should be able to solve based on what you have learned already, but it is not something that you can just regurgitate and go like, oh, if I just repeat that process that I learned in class, I'll be able to answer that question. And why do you think that is the case? Yep. Because I want you guys to show me whether you can problem solve, okay? Because regurgitating a process, just repeating steps is not problem solving. But why is that important? Why do I emphasize problem solving so much? I mean, you can probably count the number of times I type your problem solving in the syllabus alone. Why do you think that is important? Why do you think I think that is important? Yep.
We will be tackling all sorts of problems, and they could all differ.
When you're working, right? So when you work, when you get to a 4-year university after you transfer, this is the norm. Okay, because your professors at a 4-year university will be testing you on problem-solving skills because they want to prepare you for work. Okay, so when you go to work as a software engineer, do you think they will give you something that is just procedural? Tech, this is a 25-step process. Just do this 1,000 times, to all of these items, and we're good, for the day. That is not going to happen. Okay, basically anything that can be automated is already automated. Otherwise, they're not going to hire you to do something that is mundane. They're not going to hire you to do something that is repetitive. They're not going to hire you to do something that is prescriptive, okay, where you just have, oh, okay, here's the instructions, follow these instructions step by step, and you're good. Okay, you will be hired to problem solve. The first thing most software engineers or software developers do is to, guess what? What do you think they do? So let's just say that you graduated from, I don't know, CSU Sacramento, okay, Sac State, and you got hired by a company as a developer. What do you think is the first thing your boss will ask you to do? Yes?
Debug.
Exactly. Tech support and debugging, okay? Tech support means you have to collect the data of something that is potentially a problem, okay, the symptoms. And then your next job is to say, okay, so this is the source code, 20 million lines of it. Go fix this. Obviously, they won't let you change the repository because they don't trust you yet. But they will be observing how you do that debugging process. Okay? And what do you think is debugging? I mean, you guys have all taken CISP310, I hope, and you probably have encountered bugs in your program. So what is debugging?
It's just pretty much see out statements, try to find out where the variables are.
That's one way to do it. And unfortunately, my colleagues do not have time to teach you how to use a debugger, which is the proper way of debugging a program. But debugging is basically looking at a program. It has shown you evidence that it doesn't work the way it's supposed to, not 100% anyway. Okay, so there are cases where the program does not work the way it's supposed to. So it shows you some symptoms. It's supposed to give you this output, instead it's giving you some other output. So the program is not working. So your job is to fix it. Now, in CISP 360 and in your other programming classes like 400 and 430, you are debugging your program. I hope you guys are only debugging your own program and not somebody else's. But when you go out there to work at Valve, okay, Riot, and so on and so forth, those are game publishers, you'll be debugging somebody else's program. It's not even a program that you wrote. How do you debug somebody else's program? And all you can start with is, oh, these are the symptoms. People complain about, when I select this champion, this is supposed to happen, and instead that happens.
You unit test, like just test individual pieces of the code.
You can unit test, but you can also try to deduce what is the last line of code or the last block of code that is supposed to control that behavior. What is the last point of decision, okay, where it made the wrong decision to the wrong, so that's why it didn't do what it's supposed to. But that's only a starting point, because that turning point is the result of another turning point, which in return is another turning point, and so on. So you basically have to track that backwards. You have to, in some way, execute a program backwards from the point where the symptom becomes visible to the point that is actually causing the problem to happen. Now, if you're working with something that's deterministic, okay, which means every time this input you present this input to the program, it gives you that output, you're lucky. Okay, that's really good because now the problem is very reproducible. Okay, this input always creates that output. That's ideal. Okay, this is like a walk in the park, because there are problems where it is not reproducible. Okay, some of you may get into real-time systems, robotics, or anything that is asynchronous, which means your program is interacting with something else where the timing is not controlled by your program. That's called asynchronous. So when you're dealing with a program like that, then it's a lot harder to debug, because now it depends on the interaction of all the external stuff and the timing of that. If the timing is off, the symptom is different. It may happen like 3 times in an hour in a row, and it doesn't happen for another month, and it happens again, and it's a different symptom. It looks different. Those are much harder to fix, okay? And this is what you're going to do as an entry-level software developer or software engineer. And what do you think is going to help you get this done? The debugging. How do I fix the problem? How do I fix the program?
Problem solving. Problem solving.
Problem solving. You have to do it step by step. You have to understand the code and actually to try to figure out, okay, this is what I'm seeing. This is factual. Okay, what leads to that point? Okay, what is the code that is immediately causing this to happen? Get to that point, right? Use a debugger, look at all the variables. Are the variables having the value that you think they should have at that point? No, this one is wrong. Okay, this one has a value that is not what I'm expecting. Okay, who touched it last? That code over there. Okay, that may be the problem. So you kind of have to learn the dependency and then track the program in a backward manner. The other approach of debugging, which I have observed as a TA at UC Davis, is called the infinite monkey approach. Some of you are giggling because you already know what that means, right? What is the infinite monkey approach? Go ahead.
Give infinite monkeys enough time with a typewriter, they'll eventually make something good.
Yes, or in this case, eventually fix the problem. Yep. An infinite number of monkeys making random changes to a program will eventually fix the program. Yes to quantum computing, right? Not only are these monkeys, these are quantum monkeys. They can superposition on top of each other and so on. That is, I observed this, in a class that is equivalent to our CISP310 as a TA at UC Davis. And I was going to you guys are not going to be able to get this done. So I think I hope that you guys are now understanding why I emphasize problem solving so much. Okay, so you guys may say, but Tech, you keep talking about problem solving and how important it is, and how we're going to be tested to see whether we can problem solve. Are you going to teach us how to problem solve? I certainly hope so, because I'm going to give you guys some additional slides, additional material if you want to kind of go through that and see what is useful to you. And I will also be writing code in class. Okay, at the after the eighth week of this class, I'll be starting to write code. And as some of you might have who have taken my other classes, you would know that sometimes I hope my program doesn't work, because then I can genuinely show you how to debug a program. Okay, because it cannot be canned. Okay, if it's canned, then it's like, oh, but Tech, you already know what the program is supposed to be, and you just intentionally mess it up so it doesn't do it. Okay, so I'm not demonstrating anything in that case. But if a program doesn't work because I really just made a mistake, then I can actually show you how to think about it and how to debug a program. All right, so are we good so far? All right. So at this point, we are done with the syllabus, and then we are going to move on to the actual content of the class. But before we do that, I am going to take a roll. Okay, does everybody have a computer that can sign on to Canvas right now? Because if you guys cannot, then I'll take a roll in a different way. Is that okay? All right. I'll give you guys enough time to do it. You can use a mobile device too. It just relies on Canvas. It doesn't need a whole lot of stuff. Or I can just give you like a really long period of time to get this done. So I'll just give you a lot of time. So this way you're not in a hurry to do it. So the typical way that I take role in this class is to make a quiz activity. It's not really a quiz. It does not really count to your score at the end of the semester. It's just a way for me to tell whether you are here or not, whether you know the answers of these questions or not. So typically, this is what it looks like. It's just, what is the role-taking word? In this case, the role-taking word is Logisim. So I'm going to write it on the whiteboard. So this way you don't have to scramble later on to find out what the word is. So I'm just going to write it on the whiteboard. And that doesn't. It's the trash can. All right, so try another one. There we go. Logisim is the word. And I'll give you guys plenty of time. It's not released yet, so you guys cannot see it yet. So let me give you guys plenty of time. Well, since it's the first day of class, I'll give you the end of today. I think that should be enough time. There we go. So it's available until 11:59 p.m. Save and publish. Oh, lock date cannot be before due date. Oh, it's probably the AM, PM thing. No? Oh, it's 19 instead of 59. There we go. All right, so it is published, and I can move it so it's easier to find it. But you should be able to find it now. It's just a 2022-0822 roll taking. It's under physical states, gates, and numbers. So once again, you have plenty of time until the end of today to do this. The word is Logisim or lowercase. So as long as you do it sometime today, it's going to be okay. You'll be counted as present in class. All right. So, and someone may say, but Tech, you only got about 10 minutes left. Nope, I actually got the entire lab following the lecture. So that's what I'm going to do today, is to use some of the lab time for lecture just so that we have a good head start to cover the material of this class. All right. So now we're moving. Let me go back so that you can see where I got there. So now we are moving on to physical states, gates, and numbers. And it's a really long section. This class, the title of this class is being changed, okay? It's not changed yet, but right now it is called Assembly Language Programming for Microcomputers. What is a microcomputer? Do we even use that term anymore? Go ahead.
Is that kind of like a Raspberry Pi?
A microcomputer is actually how people refer to PCs, like in the 80s. Yeah, so it's a term coming from the same era as disco. It's really out of date, okay? The reason why you're in this class is because a lot of UCs and CSUs, they are starting to use what we call the CID system. So this way, community colleges, CSUs, and UCs can have a common ground and say, okay, what is entailed in this particular class? So they have templates, and those templates, one template is for something like this class, but they're calling that class. Okay, let me just look it up for you because this may be important for those of you who are planning to transfer. So if you just look up CID comp 142, that is the ID of the template for assembly language programming / computer organization or architecture. So if I just look it up, because I want to show you what is supposed to cover in this class and why that is the case. And, oh, it's just a download. Let me see if we can. All right, bye. Nope, that doesn't show me the content. All right, so I'm not going to spend too much time on this one, but the content of this class is supposed to also include computer architecture, or what is inside the computer and what is inside the processor. I think besides myself, most other instructors of the entire district, they're still teaching this class the same way as it was a few decades ago. Which is okay. I mean, that might actually prepare people, sufficiently for UCs and CSU, but I really want to make sure that the entire content that I'm supposed to teach is also covered. So, with that in mind, the first thing is we're going to get into this notes here, which is physical states, truth, numbers, and computers. So one thing you might want to do is to kind of jot down in your notes, at 11:40-ish, Tech is starting to talk about the actual content of this class. So this way, if you're watching the entire video recording, you can skip the first portion, just skip the whole thing, and then you can just land here. And I will give you guys, some break, before we resume the discussion, because I know, a 3-hour lecture is a little bit much. I used to take this class as a 3-hour lecture. It's once a week, 3 hours of lecture, and no lab at San Francisco State University of all places. So there we go. But we'll get into the topics first so that you know what we are going to talk about. And then we'll take a short break and then come back here at about noontime. So this gives you guys a little bit of time to get some water, go to the bathroom, just walk around a little bit. So what this is about, what this entire topic is about, the first portion has to do with what is inside the computer. Now, most of you know that modern computers are getting faster and faster because of what? Moore's law. Okay.
Also,
Yeah.
that's into maybe again quantum computing or other or superposition.
Okay, so quantum computing is not quite here yet, okay? So there are quantum computers, but they're not common. So all of you guys are using, basically, quote unquote, classic, computers. So why are things going faster and faster? You mentioned Moore's law, great, okay? But what is it describing? What is Moore's law describing?
It's getting smaller. And microchips are getting smaller, and they're going faster. And if microchips getting smaller, you can, like, into like computers, you can add more microchips. It could be in that way, or superposition, or like
Stacked, you mean?
stack. Yeah, stack.
Yep.
Sorry. Yeah.
Mm-hmm. So that is right, okay? So basically, transistors are getting smaller and smaller. Okay, the number of transistors in a modern processor is insanely high. Okay, you can look at not anything. I mean, just my Fitbit. Okay, if you look at the Fitbit, it can probably run circles around a mainframe computer from the 60s. An entire room full of computing equipment cannot match the computation power that I have on my wrist. And it lasts 5 days. Okay, the battery lasts about 5 days. Okay, and those entire room of mainframe computer, guess how much power they're going to use? A lot, right? So what has changed? The answer is interesting. Not much. Okay, if you go to IBM and you ask the IBM people, so this is a mainframe that you used in the early 60s, and this is a mainframe from today. Can we still run that COBOL program, which is an entirely different topic, but interesting one? Can we still run that COBOL program from the 60s on this super duper spiffy new mainframe computer? The answer is, yeah, sure. It's just going to run like a whole lot faster, but it will run. So, okay, so what has changed? What has changed is the size of transistors. That's it, okay? That is the one driving force that makes computers becoming so fast, so power efficient, and so on. Okay, so this particular topic starts with a discussion of the various devices. I'm going to skip through a bunch because we don't really use those anymore. But we're going to get down to transistors. So now we're going to say, okay, so but how do we compute using just transistors? So that becomes a question that I'm going to answer at about noontime. And then once we answer that really kind of fundamental question of how do we compute using transistors, then we'll get into logic gates, okay, which basically roughly translates to the logical operators that you have learned in CISP310. So the or, the bar, right, the and, ampersand, and the exclamation point, which is negation. So how do we do those things using just transistors? So that's what today's lecture at about noontime is going to address. I'm really hoping that we can get to logic sim because that's when you actually can make your own circuit using transistors and play with it, test it, and so you can then visualize. You can actually say, oh, so this circuit, which I can actually make using real transistors, using a circuit board, would do this really simple logic thing. But then everything inside the computer is made out of simple things. There's just a lot of little simple things inside the computer. So collectively, they can do all the fascinating things that we can do now. All right, so I'm gonna give you guys time to kind of pause, relax a little bit, and let's just say that we're gonna resume at noon. Okay, so I'm gonna pause my recording. Nope, there's no way to pause it. Okay, never mind, it's okay. Yeah.
Do you mind if I come in 5-10 minutes after that? There's a phone ready that I was asked to attend, but
Okay, yeah, that would be fine.
appreciate it.
So you probably want to take a note, so you can just rewatch that portion of the recording.
Yeah,
Yep.
I
Okay.
haven't read the module before class.
Okay, excellent. I'll be staying in the classroom, so if you want to go outside to go to the bathroom, I think your stuff is safe here. So how many of you here have taken a class from me from before? Okay. Was it online? Yeah, so I can't really tell.
It was the one with the logical things. You had to like write
440?
out. You had to write out the stuff.
440?
Discrete
so.
data structures?
Discrete structure.
I don't remember which one it was.
Well, I only teach 2 classes, 310 and 440.
Probably was that.
Yeah.
I'm thinking 440 with you at 3 o'clock as well right now.
Yep, that's later today.
Get through, yeah.
Yep.
The final was a bit rough though.
Hmm?
The final was a bit rough though for me.
For 440? Well, it's really testing that problem solving thing.
Still did well in the class though.
Hmm?
I still did well in the class though. I tend to do it.
Yeah, I curved it for the opposite reason. If I see the best score of the entire class is like 75%, I just rescale everything.
Out of curiosity, did you know like difference between like scores, asynchronous and like in person? Is there a big difference at all or no?
In terms of scores?
Yeah.
Yeah.
I imagine the in person is dramatically better to some extent.
I wouldn't say dramatic, but it
It
is
is better.
significant.
Yeah.
Yeah.
It's so easier to stay focused like this.
Exactly.
Yeah.
I think there's a lot of focus issues.
Yeah.
With online classes, I think some, obviously not you guys, but some students, basically they refuse to take notes in a defiant way. It's like, if you tell me what to do, I'm just not gonna do it. I'm not gonna do exactly what you tell me to do. It's like, okay.
I had to learn how to use OneNote. So I was taking a physics class during this time. Like OneNote with like a proper like a pen, like an online pen. That's what I learned how to do over the pandemic. Otherwise, notes online are
Yep.
interesting.
Well, writing notes, I find, since this is just chit chatting. If you guys don't want me to chit chat, that's fine too. So just 2 weeks ago, I was going camping or cabining with a family friend.
Yeah.
He works for the Lawrence Livermore National Lab. So from the outside, he and I are very similar. Kind of geekish, nerdy. Just kind of like to solve problems. But we took notes, in different ways, and we processed, lectures differently. He has this dyslexia, so he has to read ahead of time, the material, and he takes very complete notes, every other line, so that after class he has time to go back and then kind of add insights, connections, and whatnot to his existing notes. I have ADHD. So I don't read ahead of time.
Yeah.
I go to every single class and go like, this is new, this is fresh, this is exciting. Professor, please teach me something fun and new today. If I read the book ahead of time, that takes off like a good portion of the excitement, and then just go like, but when I wrote notes, I would go to the bookstore and buy wide rule paper. And the way I wrote my notes is I would put a line in the center of the page, so it's double column, and then I write 2 lines per line actually on the paper. I write really, really small. And I don't really go back to my own notes much, after I took the notes. So note taking to me is a way to pay attention. There's a point of focus. Okay, so that's interesting. What the professor said, I connect this to some other concept, I write it down. I use a lot of abbreviations, a little incomplete sentences and whatnot, but it's just a way for me to stay focused in class. But I absorb, most of the material during the lecture. He does not. He pre-reads, take really, really complete notes, and then he goes back to reprocess those notes. Entirely different process, entirely different personality, but one thing is common: notes help. Yep.
I normally just write them down and then I don't look at them again.
Yeah, which is fine because you're still using note taking as a way to focus so that you don't get distracted. So your mind stays on the subject matter.
Also, yeah, online and in person, like the test scores are different for physics. They're like 30% lower.
Yeah.
From like 60, they were like 30 averaging. Yeah.
421.
Same class?
Same class. The teacher was like, this isn't working.
Yeah, it depends teacher.
Was it synchronous or asynchronous?
So the tests were in person, but all the stuff was online.
But was the instruction itself synchronous or asynchronous? Because I'm synchronous.
I think it was ace.
If it was online, that would be
Yeah, it was just all the videos were online.
The
yeah.
majority of online classes are asynchronous. I'm one of the few people who do synchronous.
So, like,
Because I'll be the first one who goes off if it's not
so all the
synchronous.
stuff was already out there mostly,
Uh-huh.
and you just had to watch the videos, which were lectures and just like.
Yeah, but that just is not just for me. For people like me, for people with ADHD, there are too many shiny objects around. So without the structure of I have to be at a certain place at a certain time, in a certain room, to learn something. Without that structure, I'll be lost. I'll be going like,
Yeah,
I can do this tomorrow.
In
And then-
person, yeah, I prefer it.
Yeah.
Well,
Because of that reason.
the style of notes, what I mean by that is like, just typing, or do you have to write your notes down, or typing also like?
They say
typing
writing
your
is
notes
better.
Any different for you? Does it affect you any different or no?
Well, I'm old.
Okay.
Well, they also say writing's better.
It is better, that's what I
Because
experienced.
you like remember more stuff.
typing notes.
It depends because if you have complex stuff, writing gives you the flexibility, but you lose the speed.
Yeah, definitely.
So if you want to be able to capture a lot of stuff, you can type. But the problem with typing is in the math class, it's harder to capture the integration and whatnot.
Yeah.
So if you learn how to use LaTeX, which I have learned over time, if you're proficient in LaTeX, then you'll be fine. You'll just be able to capture all the equations, in the same way that the teacher presents it. So but I think in my time, I didn't have an option to do it electronically, so it's all written.
I'm generally a slower typer, so just like writing and stuff.
Oh, okay. Yeah, I'm much faster when I'm typing. Someone also told me that when people type, because they can type so much faster, they have more of a tendency to capture verbatim what the professor is saying, as opposed to the thoughts, of the person. So, so there's a potential downside of typing.
I could think faster than I could type.
Yeah, same here. I can
So I
think.
skip words.
I think the thinking part is the slowest part of my head, because I cannot talk any faster than I can think, and that's why I talk slow. Some people can talk really fast because they can actually think faster. Some of this has to do with your personality type too.
So that personality, at least the computer science personality test you posted, that was interesting. It was the IBM one,
It's MBTI.
MBTI, yeah. That was interesting.
Yep. It's not scientific. In other words, there's no empirical evidence of any of that, but it's kind of interesting. At least from the sense of the letters that you're getting is basically a reflection of how you answer the question in the questionnaire. And I find that there's some general truth to the characteristics of the types. The friend that I was mentioning is an INTJ, and I'm an INTP, so off by just one single letter. But we are very different underneath, so-called under the hood. But from the outside, people can easily mistake me and him being of the same type. It's kind of like looking at the Volkswagen Beetle, the current one, versus the the Bug from the 70s. So when you look at the styling and the outside, you go like, yeah, kind of one is just a spiffier version of the other one, and then you look under the hood, it's like entirely different. Where's the engine? Where's the coolant? Because they are entirely different cars. One is rear engine with an air-cooled engine, right? And then the other one is basically just a Golf, just styled to be a little bit more round. Somebody has to make a e-bug using the old chassis, the rear engine, but turn it into electric. That would go really fast because it's a really light car to begin with.
I was watching this video series of this dude turning a old military Hummer
Uh-huh.
into like electric Hummer, and
That will take a lot of batteries.
I think the channel is named Jerry Rigs Everything or something.
People take the batteries from the Teslas and they'll put them into some other cars. Like someone has like a video of someone has like a really old Ford truck and they took the engine of like the Tesla and they put it in the truck. And so it looks like a really old beat up pickup truck from like the 80s. And then you open up the hood and then it's like a Tesla engine.
It's a motor. It's not even, it doesn't take up much space. It's just a battery that takes up a lot of space.
It's like really small, like the compartment. There's like a lot of brackets holding everything up, but the whole, like you pop the hood open and it's mostly empty. It's weird because it doesn't have like, it has like a smaller like engine and stuff.
The Teslas are interesting from many different perspectives. How fast those cars are is just mind-boggling. Because I think the Plaid, is it called the Plaid edition?
Plaid?
Plaid? Yeah, so they have a 0 to 60 of 2 point something seconds. Now, yes, I do understand you're talking about $150,000, probably close to $200,000 car. But, outside of electric cars, $200,000 won't buy you a car that fast. Not a Porsche, not a Corvette, none of those gas cars can even get close to 2 point something seconds because without transmission, it just keeps going. It just keeps accelerating. All right, so we are back. Maybe a few people need to come back a little bit later. All right, so I did not stop the recording. So if you're watching the recording, on YouTube, this dead time is there. So it's just kind of account for the dead time. But since I recorded from 10:30, you can just calculate the offset. Just kind of say, okay, this class is restarting at about hour and a half point. Okay. All right, so we're gonna dig into some of the more technical stuff now. So I'm going to skip, the first few portions. For those of you who are curious, you go like, well, we have transistors now, but what do we do without transistors? Then you can go ahead and read some of these sections, but I'm not going to test you on, okay, show me how you would wire up relays to make a computer. Okay. That's going to be a pretty chatty computer, a lot of clicking, like that. But you can, okay, because in reality, question?
Oh, I'm just on my sound.
Oh, hi. You're
Colton from your online classes.
Oh,
A
great.
year and a half ago or so.
all right.
So I see the man, the myth, the legend in action.
Oh, okay. Yeah, that's what online classes do, right? You get to see me all the time because I have a little webcam thingy, on the side, but not in person. In person, you're like, oh, Tack is really that short. Yes, I am. I am really that short.
You did seem bigger when all we could see is your face.
Exactly, because all right. So you guys have taking classes together. Nice. If you want to hang out, you can just find a seat if you want. Yeah. I probably have to remove that portion from the recording because otherwise the district will be on me. It's like, Tack, what are you doing, man? You're vaccinated, right? You're clear?
Yeah.
Okay. That's the only concern that I have. The district probably has some other concerns. All right. So I'm going to skip over the electromechanical, chapter or section. But for those of you who watched An Imitation Game, the movie, this section is kind of interesting because that's what Turing did when he worked on the computer that's designed to decipher German encoding. Okay, so from a historical perspective, this is kind of interesting, but for our purpose in this class, it's cool but not totally relevant. And then we move on to vacuum tubes. Once again, before transistors, we have something like transistors. They're called vacuum tubes. So one thing is really important to understand about computers, okay, is whatever device you use to make a computer, there are only like several properties that needs to be there, okay? You need to use the very same quantity that you are switching on and off to control the switching itself. That's it. It can be hydraulic. It can be pneumatic. Hydraulic means you have a fluid, right? So you have a valve to control the flow of fluid, but in return, the valve itself is also controlled by pressure of the fluid. Okay, so as long as the controlled physical quantity or physical phenomenon is also the same phenomenon used to control the valve itself, you're probably okay. Okay, yeah.
I kind of don't understand that. What do you mean the same as the controller?
So if you look at a typical switch, you are clicking it on and off, right? So that is not the same kind of physical quantity because it's mechanical to turn it on and off, but what is actually controlling, what is switching is electrical. So what you need is something that is electrical to control whether you let electricity pass or not. A relay is one of those devices, right? Because a relay has an electrical input and it switches on and off, whether you let electricity to pass through it or not. So a relay would meet all of those requirements. Is that okay? Sort of?
Holly's just got a note. Come back to this later.
Yeah, we will come back to this later when we get to transistors. When I describe how a transistor works from our perspective, then it'll be pretty clear. So vacuum tubes is also one of those devices. It's just that vacuum tubes take a lot more power. Can anyone? Okay, has everybody seen a vacuum tube in action? No one, very few. Okay, no audio files here. Okay, so a vacuum tube looks like a light bulb. It glows a little bit because you need to get the temperature up in order for electrons to be free. And once electrons are free on a conductor, you put a charge, a positive charge on the other side. The electron will travel through vacuum and hence vacuum tube because inside is vacuum. So electrons can actually travel through vacuum space if you heat up the filament, and then the electrons will be attracted to a positive charge. It would just fly over vacuum to the other side. So that's the basic principle of a vacuum tube. But they can also be used as valves. Okay, they can be used to turn on and turn off electricity. So they can also be used for the purposes of making a computer. Obviously, if you're using vacuum tubes instead of relays, your computer is going to be faster because there's no mechanical components. It's not going to take 20 milliseconds to go from this contact point to that contact point. It's going to be a lot faster if it's a vacuum tube. So we're not going to talk too much about this, and then we move on to transistors. So transistors are what we call solid state. It's based on semiconductors. Okay, so how can something be semi-conducting, right? You're either conducting or you're not conducting. How can something be semi-conducting? That semi-conducting part is basically the switch part. Okay, so given the same thing, is a solid state is one single little thing, whether it is on or off, whether it lets current or electricity to flow from one end to another end, is controlled by the third terminal. So the third terminal can say, okay, we need to be off. Okay, don't let any electricity flow through, or can say, yeah, we're on. Just kind of pretend that you're not here, and pretend that you're just a wire connecting from one end to the other end. So I'm going to show you guys some schematics later on. So this basically talks about the physics a little bit. Not going to test you guys on the physics of a transistor in this class. But the bottom line is you can use a voltage, okay, an electric potential to indicate whether a transistor is supposed to be on, which means we are letting current or electricity pass through, or off. Basically, it is disconnecting between the two terminals. Okay. All right. So now we move on to physical states. So once we have the discussion of transistors, then the next question is, okay, but Tech, I'm still not really seeing how transistors can be used for computing, because you probably know that everything inside the computer is binary. It's either 0 or a 1. I don't really see a 0 or a 1 if I just look at the two terminals of a transistor. So what is going on here? Well, you just have to interpret, okay? So this is about interpretation. So what you can do is now you can say, well, any voltage below this threshold is interpreted as a 0. All the voltages above a certain threshold, we'll go ahead and call that a 1 or true. So below a certain point, you can look at it as false or 0. Above a certain point, you can look at that as true or a 1. So it's really just interpretation. So that's basically what 2.2 is about. And then the true-false value is kind of the same thing. So now we've skipped all the way to section 3.1. You might want to take, just kind of jot down the note in your notes here and say that at 12:10, we are starting to talk about actual transistors. All right. For this part, I have to go slower, okay? But at some point, I'm also going to use logisim, the same word for rotating today. And once again, you have until the end of today to finish that activity. For the first day of class, I'm giving you plenty of time to do it. All right, so we're going to go take a look at what a transistor is, or transistor types. Not going into the specifics, let's discuss how to use the two types of transistors. Note there's an alternative description of transistors in logisim. Go to help, library reference, transistor. Okay, so now you guys are going like, what are we talking about? What is logisim? So I'm going to do this part here. You can write down in your notes, okay? You can also just kind of jot down the time so you can look at the recording later on, because I'm going to show you how to do this. So what we need to do is to go back to the Canvas website. And if you go to shared folder, which is here, so if you're taking notes, so there are a few things you can do right now. You can try to follow exactly the same thing, which is good in a way because that means you know how to do it. It's bad in a way because if you're falling behind, then your attention will be just going like, oh, I need to catch up, but you don't really need to catch up because this is all getting recorded. Okay, you can also just kind of write down some instruction like, okay, this is on Canvas and the name of the link is just shared folder. Okay, so this way you can follow your own instruction later on. Okay, I'm gonna right click and open in a new tab. So once you land there, let me see if I can find that file. Okay, so here's a file. Okay, the name of the file is logisim310.jar. So once again, instead of trying to follow me while I'm demonstrating, you can just kind of write down the name of the file, which is logisim310.jar. The extension jar stands for Java Archive. So basically, it is a Java file, which is the bytecode that a Java virtual machine needs to run programs, except this one is archived, which means it really is just like a zip file. It is a zip file with a funny extension. If you were to rename this file to .zip, Windows would basically unzip it, just like a normal zip file. Okay, you can actually see the source code of Logisim. For those of you who are super duper curious and just say, I think I want to know how it works, you can actually read the entire source code. All right, so you can do this on your own computer. Just download it, okay? So right click and download. Right there. Okay, so now I'm gonna pause a little bit because the computers of this lab cannot save your files in a persistent way. So when they reset, your files will be, guess what? Gone. So what you can do, there are a few things you can do. One is just to bring a thumb drive. Okay, bring a thumb drive And I'm not sure whether these things are set up to hook up easily, but the USB ports are accessible on the right side of the computer, behind the monitor. Just remember to take your thumb drive home when you're done with this class. So that's one thing you can do. Two is to bring your own device. So bring your own laptop computer. The computation requirements to get through the labs of this class is like this much. Okay, so an older computer, from like 4 years ago. This is like 4 years ago. This is from 4 years ago. Plenty of power and resources for this class, not a problem. But it's just one single file. You can just re-download it also for every single time. It is a little bit of a hassle, but it's 2 minutes, right? Maybe 30 seconds. So you can always just go ahead and re-download it. And after you download it, okay, it's scanning for viruses, and it's going to take a little bit of time. Just remember where you download it. Depending on how you set up your browser, it may just go straight to the downloads folder, or you may want to specify where you want to put it. All right, so it's downloaded right now. So in this case, it is downloaded to my downloads folder. Now, to open this file, to run Logisim, you will need Java. You don't need the latest and greatest of Java, just a slightly older version will do. So in my case, I don't really have a GUI option. So I'm going to have to do it using the command line. I will move one of my prompts to the side where you can see it. There we go. All right, so one thing you guys will notice is I'm a very CLI kind of guy. CLI stands for Command Line Interface. So I tend to type a lot. So in this case, Java is the name of the command. If you're using Windows, you can probably double click and it will run. Okay, but if you're using Linux, you may or may not have your system set up to do it. So Java, and then we supply the path. This is how paths works out in it's not okay. All right, so I am just double checking. Nope, it is. Oh, it is here. So the file is here, and if you just say Java, it's not going to work. So you have to specify dash, jar, and that's going to run the program, which you cannot see because it put it in a different window. So let me move that too, so you can see it. Give me a second, and there we go. And I'll maximize it on this side. There we go. So this is Logisim, which you'll be using until the end of the semester, right? That's what we do. It's a fun little tool. You can build circuits, tiny little circuits, or you can build an entire processor out of this. Okay, that's what we're gonna do. All right. So the first thing you might notice is there's a help, and under that we have library reference. And if you look under the library reference, which is opened up in a different window that you can see, there we go. You can see wiring library, and under that is transistor. So this is the description of a transistor from inside the tool that we call Logisim. So it's a lot of reading. Yes, this class definitely has a lot of reading. So the question is, what exactly is a transistor? So I'm just showing you where you can find the description from inside the tool. Okay, so this way you can read it offline if you want to. But what I really want to do is to do it, so that I can explain it, one step by step. So I'm going to switch back to Logisim. And actually put it in a circuit. So logic sim is a little bit dated. I think on Macs, particularly, it's really bad because the zoom control is all the way down here. Okay, so if you go to the lower left side of the screen, you will see the zoom control. It doesn't work too well on Macs. I think on Macs, somehow the text is always kind of tiny. And I'm just going to go to wiring and use the drop down, and you can see transistor here. So the way you look at this, okay, if you know what is the object-oriented programming, is what you see here, these are quote unquote classes. In other words, this is the template that you can use to create instances of these things. If you want to place a transistor into your main circuit, this is actually your program space. Okay, this is where your components go, and you can specify how they connect. So the way you do it is you click on the component, which in this case is a transistor, and then don't drag it. Okay, you don't have to keep pressing the left button on your mouse, just a little click. Okay, and then you just move your mouse pointer to the other side, and that's how you place a component or make an instance of a template on the right hand side. Are we good so far in terms of just generally how to make an instance of a component? Okay. So I'm just gonna, another click will place it into this portion here. So now we can take a closer look. The other thing you want to pay attention to is quote unquote the selection, because it shows you the properties that can be changed about the component that you have selected. Now, if you select multiple components, it will let you change the properties that are common to all the components that you have selected. So if you have a bunch of transistors selected in the main circuit, you can change all of them at the same time. So it's a time saver kind of thing. So now we have, this is a P-type transistor. So every single attribute that is displayed in selection can be changed, because otherwise it doesn't make any sense to display it here. So we're going to play with this a little bit, and we just click on this bar here, and it turns out there are two types. One is called the P-type, and one is called the N-type. The P-type P actually stands for positive. It has to do with how we dope the semiconductor material. So for us, P is positive. You just kind of remember it connects to the positive side of a circuit, and an N-type connects to the negative side of a circuit. Next, we have two controls to control how it shows up in a circuit. So if this is not the orientation that you want, okay, let's just say that we want this thing so that the arrow faces down, okay? So right now it says the facing is east. So if I want to rotate it 90 degrees clockwise, what do you think the facing should be changed to?
South.
Yep, that's right, south, okay? So instead of using degrees to specify the orientation of the device, it uses northeast, southwest. That's it. So we change it to south, perfect, like that. Now, there are 3 pins to this device. If you want to know what pin is what pin, it depends on whether it is documented, but sometimes it is and other times it's not. Excuse me. If you hover your mouse pointer to just one of the terminals, this one does not show you what it is. But for some other components, that will give you a little pop-up, and it will tell you what that particular terminal is. But in this case, since it does not tell you, I'm going to tell you. All right, so the first thing is to take a look at the arrow itself. The arrow itself is telling you the direction of flow. But what is flowing through the device, excuse me, depends on whether it's a P or N-type transistor. If it's a P-type transistor, the flow is indicating the flow of positive charge. P for positive, right? So the flow is positive charge. And for N-type, the arrow would indicate negative charge, the flow of negative charge. So the chart is always going from this end to this end here. So the where it's flowing from, which is also called the tail of an arrow, is what we call the source, because that's where the charge is coming from. And where it's going to, which is the opposite side, this is called the drain, because that's where things get out of the device. So are we doing okay so far with the nomenclature? The flow goes from source to drain, and then the type of the transistor determines what is flowing through the device. So a P-type transistor has positive charge flowing through, and an N-type transistor has negative charge flowing through. How many people have taken physics, electricity, that sort of stuff? Okay, so is it okay?
I felt more clear because of the class, but it's still not.
Okay. Well, when we actually put it into the circuit and actually make it work, it will be more clear. All right, so this is the source, this is the drain, because the source is producing, quote unquote, producing the positive charge in this case, and it's going through this direction. And this is a drain because that's where the charge is going out of the device. Then what about this guy here? This guy is called the gate, okay? Because it is controlling whether we want to allow the flow or not to allow the flow. So this pin here is called the gate. So we have gate on one side, and then we have, in this case, the north side is the source, and then the south side is the drain. All right, so what can it possibly do? Okay, let's try to figure out what we can do with this. So the first thing I'm going to do is to hook up power. So this symbol here, power, is basically the source of positive charge. So we're going to put this somewhere in the circuit. So I'm going to put it right about here. And then we're going to have a ground. So ground is basically the same thing as a negative charge for the entire circuit. So we'll stash it about here, okay? And since the flow is supposed to go from, it's going in this direction, so we can now just kind of hook it up. So to connect the connection points, there are a few things that is important. First thing is not every part of a component is connectable. So there are connection points to each single component. For instance, the tip of the triangle here is not a connection point. How do I know it's not a connection point?
Specifically with Logisim, you can hover over the tip and there won't be a circle showing that it's a point.
Yep. So if a circle is showing, it is a connection point. If a circle does not show, when you are just hovering over, then it's not a connection point. Okay. Now this is a very important part because sometimes people connect to a component thinking it's connected, but it's not, because it's not actually going to a connection point. It's just going to a pictorial part of the diagram that looks like a connection point. So once you start with this, you can now drag your mouse and make a connection, like so. And then we can also do something like this. You don't have to copy this because this is a terribly bad circuit. Excuse me. All right. So what about this gate here? How can I say, hey, since it's the gate, this is what you can control, okay? If you present a higher voltage, which is the same as the source, if you present a voltage that is the same as the power, it's telling the device to turn off, okay? I can give you a truth table later on. Dry cough, sorry. So to do this, we can use a pin, okay? This is an input pin. The square is an input pin. So what we do is we just hook up a pin to the gate of the transistor. So now we can specify whether it's on or off. So with a pin like this, we want to be able to toggle the pin. In other words, we want to change the value of an input pin. To do that, you have to change to what we call the poking tool. And officially, it does not have the name of a poking tool, but I always call it the poking tool because it's a hand and you can just use it to click on stuff. So now we can click it on and click it off. Now you can see kind of when it's a 0, there's a red Y here, and if it is a 1, it is a dark green wire. So let me tell you what is happening here and describe what a P transistor is doing. Okay, the description of a P transistor is if the gate has the same voltage as the source, then it is then it is off. It won't let anything flow through it. On the other hand, if the gate has a low voltage compared to the source, then the device is on, and it will let the positive charge go from source to drain. We doing okay so far? Okay. So whether it's on or off, once again, is basically a relationship between what we see at the gate versus what we see at the source. If they are the same, the device is off, like it is now. If they are different, if the gate is lower compared to the source, then the device is on, which means it is allowing positive charge to go through the device to the drain. Is that okay? All right. So at this point, okay, so let me just ask you a quick quiz here. Is this transistor on or off at this point? Is it connecting or is it not connecting? Based on the rules that I just talked about.
It's connecting, right?
It is, well, let's see whether the gate and the source are the same. Do you think they are the same?
Oh, yeah.
And you can click wires too. If you click a wire, you can see what it is. This is a 1, and this is a 1 as well. So they are the same. When the source and the drain, when the source and the gate are the same, the device is off. So it is off. So that's why you see a dark green wire here, because dark green means 0. And this ground is always 0. So the ground by itself is already 0. In other words, let me show you what I mean by that. So I'm going to remove the wire. Okay, to remove something, you have to go back to the selection tool. So I'm just going to remove one segment here. And you can see that without connection to the device, this wire is always dark green. Because the ground, this symbol over here, the ground symbol, is always representing an infinite source of negative charge. It's just a huge, gigantic, infinite reservoir of negative charge. And then the other symbol, which is the power symbol here, is kind of the same thing. It's an infinitely large reservoir of what? Positive charge. Okay? So one is a source of positive charge, and the other one is the source of negative charge. Negative charge is 0, positive charge is 1. Are we good so far? Okay, but Tech, what about this green thing here? What about this green wire? Green wire basically means we don't know what it is. The value of this wire is undetermined. Because at this point, the transistor is off. So there's the wire that the mouse pointer is hovering over, is neither connected to the infinite source of positive charge, nor the source of negative charge. So it's undetermined. It's just what we call floating. Are we good so far? It's analogous to, if you look at the blue section of the wire, it is analogous of looking at a piece of copper wire, and I'm asking you, what is the voltage that you're measuring on that wire when it's not connected to anything? It's like, Tech, I don't know. I mean, it's not connected to anything. That's what blue is representing. Are we okay so far? All right. And that's because the switch is off. Okay, the transistor is off at this point. So let's go ahead and turn on the transistor and see what happens. What do you think is going to happen? This is one of those things where it will help you understand material in a deeper way, is to ask the question first. Try to figure out the answer before you actually empirically find out what the answer is. So if I flip this 1 to a 0, what is going to happen to the state of the transistor? Now the gate has a lower voltage compared to the source, and this is a P transistor. So is the transistor going to stay off, or do you think it is going to turn on?
It's gonna turn on.
It's going to turn on, right? So when the gate has a lower voltage compared to the source with a P-type transistor, it's going to turn on, which basically means, oh, it's just connecting whatever is at the source to the drain. Are we good so far? So that means the infinite source of positive charge will now connect to the wire that is blue, which also means that wire is now also going to experience positive charge. Is that okay? Which means the color of the blue wire is going to change to what?
Red. Oh no. Green.
It's going to change to light green because light green represents 1, dark green represents 0, and I'm going to explain what red is representing in just a little bit. So let's go ahead and give it a click. So now the gate has a dark green color because it is 0. But the wire connected to the drain is now light green as well because the transistor is on. It is as if it is just a wire connecting straight from the source to the drain, as if it is just a single wire. Because it's on, it is connecting. Are we good so far? So now I'm hoping that some of you are having this question in your head. Then what about that red wire that we saw earlier? What is the difference between this picture and the picture that we got earlier when we had the red wire? So the red wire is there because we had, okay, let me go back to the selection tool because that's the only way you can connect wires. So as soon as I make this connection, it becomes red. What is going on here? And if you click on the red wire and ask, what is the value of the red wire? Logisim is going to tell you error, Robinson, error. And why is that the case? Okay, so think about from the perspective of a circuit. You have a switch, right? The light green, the power, is kind of like the positive end of the battery. Let's call this the car battery, okay? The ground here is kind of like the negative terminal of a car battery. The transistor is just a fancy switch, okay? And it's on, it's connecting. What happens when you connect a wire directly from the positive end of a car battery to the negative end of the same battery? So warning, don't try to do that. Never try to do that because, go ahead.
A short circuit?
It's a short circuit, yes, very good. It is a short circuit, which means what? How can we, is there anything we can observe that we have a short circuit going from the positive terminal of a car battery to the negative end of the car battery? There's no way you can ignore that because that wire is going to go red hot. Red hot, okay? That's an error state because you have what we call a crowbar. It is a condition that really should not happen. And that's why you see an E because we don't like that. Now, from the perspective of the wire, let's think about it from the perspective of the wire. The wire says, I'm a conductor, okay? Whatever I connect to, I would share that charge, right? On one end of the wire, it connects to ground. It basically says, hey, I'm connected to an infinite source of negative charge. I'm negative. On the other side of the wire, it connects to basically a switch that is on, which means the switch is as if it's not there. So the other end says, oh, I'm connected to an infinite source of positive charge. Oh, but that's a problem because now I'm connected to both an infinite source of negative charge and a source of positive charge. I don't know what I'm supposed to be. Is that okay? So from the perspective of the wire, this is why it is an error because it is connected to both directly and there's no way for the wire to determine, am I supposed to be positive or am I supposed to be negative? Because it's connected directly to both, it cannot make a decision. It cannot determine. Are we okay so far? are we kind of understanding what a transistor is and how it is acting as a switch? Good so far? All right, so we're going to complete the circuit. All right, so I am going to switch back to this mode here so I can get rid of the useless connection because that is not how we want it to be. And I can now show you guys how to duplicate, okay? Once you select one or more components, you can type Control D to duplicate. You can also use the Edit menu and select Duplicate over here. Does exactly the same thing, it's just a shortcut key. So now we have another transistor, also a P-channel MOS transistor, and I can now move the other one over here. And I look at this and go like, I want that gate not to point to the left-hand side because that makes it really kind of awkward to draw a wire to. I want it to point to the right-hand side. Okay. How do you think I am going to be able to do that? So let me click it first. Where do you start? Okay, how do you start to answer that question? I'm trying to change one of the attributes that control how the component is displayed. So which part of the screen are you going to pay attention to?
The left side.
The lower of the left side, because remember earlier we changed the orientation from pointing east to pointing south? So maybe it's one of these things that can help me flip the gate from pointing to the left-hand side to the right-hand side. So which one do you think is going to, it's obvious, which one do you think is going to do the trick for us?
Easy.
Yep, it says gate location, right? Top left versus bottom right, okay? So we're going to do that. So one thing you can do with this tool is you can just play with it, right? We are not trying to learn how to disarm a bomb using a real bomb, right? If you click the wrong button, what possibly can happen here? All right, cool. Now that just changes the appearance of the component, how it appears on the circuit. Just makes it look nice, okay? So now we need two N-channel transistors. So let's go ahead and make two N-channel transistors. So there are two ways to do this. Okay, when you get a transistor out of the template, the first one, it's going to be a P-type. So we're going to have to change the type itself, right? So we changed P-type to N-type. And we need two of these, and they have to be in series. So we're going to use duplicate, Control D, make another one, and then move this one over here, and make a connection so that these two transistors are in series. And then both of these will have to connect to the ground. Okay, so how are we going to connect these two transistors to ground? It's a question about what is going to connect to the source and what is going to connect to the drain. And this is an AND transistor. It's no longer a P transistor. So with an AND transistor, what type of charge are we controlling? Are we controlling the flow of? Negative charge, right? So the source has to be consistent with the kind of charge that you can switch. So in this picture here, where is my infinite source of negative charge? Ground, right? This guy over here. So that means the source has to connect to the ground here. But before we do that, we probably want to turn it around. And unfortunately, the wires, if you try to say, oh, we can just select the entire thing and then change the heading, it's not going to look right. I will show you what happens when we do that, and then we'll do it in the proper way. You can select multiple parts, and then go to facing, and say north, and it doesn't do what it's supposed to, because it's rotating each individual part individually. It doesn't look at the entire selection and say, oh, we want to rotate the entire selection. Nope, it's rotating, it's applying rotation to each component of the selection. So that's not going to work out too well, but it gets some parts of what we want to get done. So we just have to kind of move things around a little bit. One goes here, and I can make the other one go maybe here. That's all good. All right. So now you have to observe that the arrow or the direction of the flow is different. The P-type transistor has the flow going from positively charged to somewhere else. The N transistors have the charge going from the source of negative charge to somewhere else. Visually, can you tell a N transistor from a P transistor just looking at it? Because having to click on the transistor and then see, oh, it's an N type and it's a P type, that's really cumbersome. So is there a visual cue that we can use to say, oh, okay, I can see that one is a P type and that one over here is an N type? Go ahead.
The bubble.
A bubble, very good. So only a P transistor has a bubble at the gate. The N transistors do not have a bubble at the gate. So later on, I will explain why there is a bubble. Okay, what is the significance of the bubble? Okay, very good. So now we will finish up the connection of the circuit, like so. And you might see some wires, complaining it's red. It's okay because we're still constructing the circuit. It's no big deal. All right, there we go. And we're going to need one more input pin. And remember, the input pin is the square. So now we have another input pin. And we'll have this input pin to connect to this N-type transistor, as well as this one over here. So I did not think very well ahead of time. So now I'm going to demonstrate another thing, which is if you try to draw a wire over the other wire, are those two wires connected? That's the question. Okay, so let's go ahead and see. Okay, so I'm going to fly over the other wire and to connect it here. So now the question is, now there are two questions, because visually you just saw something happen. Okay, something go like, that wasn't there before. Okay, so that's one thing. And then the second question is, is this wire coming from the top input pin, is that also connected to the N channel or the N transistor, the top N transistor? That would be the questions in my head right now, because it looks like, well, I mean, how do we know? As it turns out, this wire and this wire are not connected. Okay. In other words, one is flying over / under the other one. Now, how do we know they're not connected?
If you hover over it, does it tell you in the program?
It doesn't.
So if you click one of the wires, will it tell you the endpoints?
Only if you use the poking tool. I will show you that later. Go ahead.
Turn on one of the pins. So I can see.
Sorry?
Turn on one of the pins.
You can use the pins, you can turn them on and off to see, but visually we can tell right now. We don't even have to experiment. You got your hand up a little bit earlier.
Yeah.
Exercising the pins.
No, it was the squares.
The squares.
The square in the middle of the wire.
Aha, the bubble, right? It's actually it is a square now because of the selection, but if it is not selected, it's a dot, right? So the dot is the indicator of whether the wires are connected or not. Okay, if there's a dot, they're connected. If there's no dot, then it's a flyover / under. Is that okay? All right. So because there's no bubble here, that means these two wires are not connected. They just appear to be connected, but they're not. Remember earlier I said, you can poke the wire and it will show you its connectivity. Let me tell you how you can do that. You change to the poking tool, which is the finger you're pointing up, and then you just click anywhere of the wire. It will highlight where it connects to. Okay? So right now you can see the highlighted portion excludes the wire coming out of the bottom input pin. So that is basically telling you, nope, those two wires are not really connected. It just looks like they're connected, but they're not. All right. All right. So I also need this wire to go to this gate here. So now I switch back to the selection tool and complete that circuit. And this is going to look really ugly and confusing, but it's okay. There we go. And it doesn't like it that way because when it's not flying over this one, it is actually connecting. Can someone tell me why it's connecting? Because that didn't happen last time. Why is it making a connection here when I was intending to fly over?
Does it have something to do with the charge itself, the type of charge?
Not exactly. It has to do with, this turns out to be a connection point of the N transistor. So if your wire is going past the actual connection point of a component, it will make that connection, even if that is not intended.
What do you mean, the endpoint of it?
Okay, let me change the layout of the circuit just a little bit. So you can select multiple components and then move the entire selection down or up. So I'm just going to move the entire thing down a little bit. And also the transistor here. Okay, I know it looks ugly. Okay, so if I just go up a little bit here and fly across, then it's a flyover. On the other hand, if I go below just by one slot, it is connecting. And the reason has to do with this point here turns out to be the connection point of this transistor. Okay? So you have to be careful because in some other exercises, in past classes, some people got into this problem, making connections when they're not supposed to be there. So then I'm gonna go through this like that, and we are technically done with the circuit, except there's no output pin, right? If there are input pins, you guys would be expecting, well, I think there should be an output pin. Because if all we have are input pins, there's no need to call them input pins. We just call them pins. So the term input pins means maybe there are just other types of pins called output pins. And their output pins is a round thing. And output pins are very simple things conceptually, because all they are is really just a way for you to see the value of a wire. So in this case, we want to see the value of the wire, which is connecting between the top two P transistors and the bottom two N transistors. That's the output. All right. Are there any questions about how I constructed the circuit in terms of procedures and in terms of using LogicSim before we go in and try to analyze what this circuit is actually doing? No questions? All right. So let's go in and actually try to figure out what the circuit is actually trying to do. If we don't have enough time to do the lab today, I'll just make it due right before class on Wednesday. Okay, because I am capturing the entire process of doing this, so it's doable for you guys just to repeat the process. Okay. So then we look at this and we go like, what is it doing? I mean, is there anything? Why is the output 1? Okay, that's the first question. Both inputs are zeros. Why is the output 1? So what you need to do is to look at all the transistors one by one and try to figure out whether it's on or off. So we're going to go do that, go through each transistor one by one. Look at this transistor here. First of all, what kind of transistor is it? Is it a P or is it an N? It's a P transistor. Very good. Is it on or off? How do we decide whether a P transistor is on or off?
You look at the switch.
We look at the gate.
The gate.
And then we compare the gate with the source. If they are the same, the transistor is off. If they are different, the transistor is on. So at this point, do you think the transistor is on or off? It's on because the gate is a 0, but the source is a 1. They're different, and as a result, the transistor is on. When the transistor is on, it is making a connection between the source and the drain, as if it is just a wire connecting between those 2 points, right? And then we look at the other P transistor, same situation, right? Even though they are coming from different pins, it ends up with the same situation because the gate of the transistor that I have selected is also on because the gate is a 0 and then the source is a 1. Okay, very good. What about the other 2 transistors, the other 2 AND transistor? Look at this transistor here first. Is it on or off? You look at the gate, it's a 0. You look at the source, it is also a 0. As it turns out, AND transistors also have the same thing. If the source is the same as the gate, it's off. So this transistor is off. It is as if there's nothing there, okay? Well, if there's nothing there, then this transistor cannot do anything, right? Because there's no negative source at the source pin of this transistor because this guy is cutting off the infinite source of negative charge already. So it doesn't really matter what this transistor is trying to do. It doesn't have a way to connect to negative charge. All right, so now we know which transistor is on, which transistor is off. So now we try to look at it from the perspective of this wire. This wire, the output pin itself is nothing more than just a place on a circuit board where you can hook up a multimeter to see, oh, does it have a high voltage or does it have a low voltage? So the output pin is really just an interface for us for observation purposes. So now we go to this junction point here. It can go north, it can go south. So you have to analyze both of those connections. So we'll analyze the connection to the south first, which is basically asking the question, where can it go, when it's heading south at this point here? Is there a way to connect to the source of negative charge? How can it connect to the source of negative charge? It has to get through both AND transistors, right? And one of them is off already. We know for sure the bottom one is definitely off. So that means, nope, there's no way for this connection point to connect to the source of negative charge. Is that okay? What about the other side? What if I get to this point here and I try to make a turn to the north and ask, well, can I connect to the source of infinite positive charge? Well, in fact, we have 2 ways, right? Because both the P transistor to the left and the P transistor to the right, they're both on. I got 2 paths to connect to the source of positive charge. So as a result, the wire that connects to the output pin is positive. It is a 1 or true. Are we okay so far with this? So now I'm going to ask you a different question. And I want you guys to think about it a little bit first before you answer. What if I click on this pin here using the poking tool and turn this 0 into a 1? What is going to happen to the transistors? And as a result, what is the output pin going to do? Yep.
It's going to turn on the N-type transistors and connect the wire to the negative charge.
Okay, very good. So if I click on this input pin, then the bottom N transistor is going to turn on, right? Because the gate is a 1, will become a 1, and then the source is still a 0. They're different, so the bottom N transistor is going to turn on, meaning that it becomes basically just a wire. It will connect the negative charge through the source to the drain of the bottom transistor. Okay, that's good. What about the top N transistor. So in that case, the source of the top N transistor will now be connected to the source of negative charge, right? What about the gate of the bottom N transistor? Would that change? It's not going to change because I'm not changing the input pin that connects to the gate of the top N transistor. So that would remain as 0. So that means I have a source of 0, the gate also of 0. When the source and the gate are the same, is the device on or off? It is off. So that means I got past the bottom transistor, only to be disconnected by the top N transistor. So there's still no path for the output pin to connect to the source of negative charge, which we call ground. Is that okay? So now we try to analyze the other side and ask what is going to happen to the other side. This pin connects to this P transistor. So how is it going to change that P transistor? So if the top input pin becomes a 1, then the gate and also the source of the left P transistor will become the same. So is that going to turn on or turn off the transistor? It's going to turn it off, right? Okay. So that means the left path to the source of positive charges will be gone. What about the right one? It remains as is, right? Because the right one is connected to an input pin that I do not intend to change. I only intend to change this one here. Okay? So now I'm going to click it and we'll find out what happens. Go like, okay, so it doesn't do anything to the output pin. But that's because in this scenario, the output pin still finds one way to connect to the positive charge. The left path is gone. Okay? You can see it has a blue Y here to basically say, I'm off, just pretend that I'm not even here. But the right P transistor is on. This guy is on. So we still have one of two parallel paths to connect the output pin to the source of positive charge. But why are we not seeing any red wires here? Why is there no error? Because one of the bottom N transistors is on. The bottom one is on, and that's why you can see the dark green wire going from the source to the drain, only to get into the source of the upper or the north N transistor. So now we have to look at the north N transistor and say, are you on or off? The source is 0. The gate is also 0. So the top N transistor is off. Well, we kind of need both of these guys to be on in order for the output pin to see the negative charge. So if one is off, nope, it's disconnected. And that's why the output remains as a 1. Are we okay so far? All right. So if I were to reverse these two, the top one being a 0 and the bottom one being a 1, what do you think is going to happen? Just looking at this from the perspective of the output pin. Nothing, exactly. Nothing is going to happen because the circuit is symmetric. So if I just do it like this, okay, we still have an output of 1 because this time we have the bottom N transistor being off. So even if the top one is quote-unquote on, which it is not, it doesn't make any difference because the bottom one is off already. But then this time we have the left P transistor being on, the right P transistor being off. Yeah, we lose one of the two paths, but it doesn't matter because they are parallel. Are we good so far? So in terms of a parallel circuit, it's kind of like a logical OR. If at least one of them is on, we're good. In a series, it's kind of like a conjunction. If all of them are on, we're good. But if at least one of them is off, we're off. Is that okay? All right. So now, the only thing we haven't really explained or tried is to have both input pins being a 1. And in that case, the output becomes a 0, because now it has lost both paths to the positive charge, and it has both of the N transistors being on. So now we have actually a complete path from the output pin to the source of negative charge. So this is the only time when the output pin is a 0 instead of a 1. Are we doing okay? All right. So the only thing left in the circuit that you have to do is to turn this into a multi-bit, input pin and multi-bit output pin. It's explained in the lab instructions already, but I'm going to do it so that you have an idea of how to do it. This is a single bit input pin. Now, how do I know this is a single bit input pin? How do I know anything about any component once it's selected? Which part of the screen do I pay attention to?
On the left side?
The left lower portion of the left screen here? Yeah, exactly. This is kind of like a list of properties of an object in object-oriented programming. So we have facing, which is just kind of superficial. It changes the heading, the direction of the pin. It's not an output pin. This is an input pin. Okay. Look at this, data bits. So as it turns out, you can actually change the number of bits represented by an input pin. So in your lab, you have to change it to 8 for testing purposes. And then right away, we got a problem, okay? Orange wire means we have incompatible widths. Why do we have an incompatible width? Well, it has to do with when your input pin is a multi-bit thing, then the output or the wire connecting to it is no longer a single wire. It is a bundle of wires. It is representing 8 individual wires, each one being a 0 or 1. But the transistor gate is saying, just give me one input, 1, 0, or 1. But the other side is saying, oh, I'll give you a bunch of zeros and ones. So that's why we have a problem. There's an incompatible width. And the same thing, if you do the same thing with the bottom pin, same thing. And so now we need to find a way to fix this problem. Okay, and then the output pin, we're going to do exactly the same things, because messing up the circuit in only one portion is not enough. Let's mess up the entire thing. There we go. Now we got the entire thing messed up. But the solution is the same. Because what we are looking at here is, okay, let me disconnect just one segment of a wire. Let's say this one here, and let's say this one here, and this one is the long one, which is here. Okay, so what is coming out of a multi-bit thing is multi-bit. So if you look at one bit as one single trace or one single wire, then what is coming out of a multi-bit input pin is no longer a single wire. It is a bundle of wires. Think about all those wires inside the Cat5 cable, except in this case we got. Are there 8 wires inside a Cat5, or is it 6? I can know 8. Okay, perfect then. So now we are saying this is a Cat5 cable, and on the other side I just need one wire. You cannot just say, oh, just strip all 8 wires, connect all of them and stick it into the wire. That's not how we want to do things. In other words, we need a way to say, okay, which one of the 8 wires do you want to connect to that one little wire over there? Okay? And, well, that component is listed on the template side here. Which one do you think is going to get the trick done? We got 8 wires as a bundle on one end, and we just want to be able to say, I just need one of these things to connect to the other side. So which component do you think will get this trick done? Yep.
The bit extension or the bit extender?
No. A splitter, exactly. Okay, so I got 2 people raising their hands at the same time. It's the splitter, okay? So splitter can do the trick. So we'll go ahead and place one splitter into the circuit just to see what it looks like. This is what it looks like. So in this case, the merged side is on the left, where the circle, the hovering circle is located, and then this side on the right-hand side is the split end. So what a splitter is exactly what the name implies. It splits. You give it a Cat5 cable, it say, okay, so how many ends do you want on the split end? You can say 1, you can say 2, you can say up to 8, but each one becomes an individual wire they can hook up to other things in the circuit. So one thing you can do when you're playing with it is you can control, there are two controls here. You can see there's one property called fan out, another property that is called bit width. Bit width is basically saying on the merged end of a splitter, up to how many wires can it handle. So in this case, we have a Cat5 cable, which has 8 individual conductors. So what do you think our bit width should be?
8.
8, exactly, okay? So the number of wires on the merged end is what the bit width is controlling. Okay, so let's say 8, there we go. And then we ask the question of, then what about fan out? What is the fan out thing you're doing here? And you can see, right now we have 8 bits, right? But it has a fan out of 2, which means out of those 8 bits, I have to come up with 2 terminals on the other side. Wait, 8 divided by 2 is not 1. So I cannot just have one single wire to one end, on the split end. So now you have a lot of flexibilities. See this bunch of stuff here? Bit 0, top, bit 1, top, da da da. That's giving you the flexibility of going, bit 0 goes to the top of the split end. Bit 1 goes to the top of the split end, and so on. So you might ask, can I make something that's really kind of awkward, like even numbers and odd numbers? All the odd numbers go to the top split end, and all the even goes to the bottom split end? The answer is, yeah, absolutely. Just click on the drop-down boxes. Bit 1 is odd, goes to the bottom. This one goes to the top. This one goes to the bottom, and this one goes to the top. I mean, you guys can play with this. I mean, that's kind of the idea, is you can play with it. So now, when you look at the description of the splitter, now we have bits 0, 2, 4, 8, 4, 6 on the top, okay? So that means the top is now a bundle of wire of 4 individual conductors. And then the bottom one has 1, 3, 5, 7, which is the alternate, the other wires. So one Cat5 cable coming in at the merged end, 2 wires coming out of the split end. The first wire of this top split end corresponds to bit 0 of the input, and so on. So this can be very, very arbitrary. But some of you caught something earlier. You go like, it has top, it has bottom, but there's a third option, which is, did you guys catch the third option when I was playing with the drop-down box? It was none. But we haven't played with that. Okay, so let's play with that. So now we will go like, okay, let's make everything none. None, 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 and none. And look at the splitter, what it looks like now. It says the top split end connects to bit 0. The bottom split end doesn't even connect to anything, because you basically specify none of the merged end bits is going to the bottom split end. Are we doing okay so far with the concepts? And some of you guys are going to say, but heck, then what is the point of having a fan out of 2 when only one of the two split ends is being used? Well, you're absolutely right. There's no need to have 2 fan out of 2. We can have a fan out of 1. And this is the one part of LogicSim that I really don't like is whenever you change the fan out, it will try to be smart and say, oh, let me reassign all the bits for you. And it will just reassign everything to the one single split end in this case. You go like, no, I don't want that because I want everything to be none except for bit 0. So that is how you configure a splitter to single out the wire or the bit or bits that you want on the split end. All right? So the way this splitter works right now is you have a Cat5 cable with 8 conductors going in, and the 8 conductors are labeled 0, 1, 2, 3, 4, 5, 6, 7. The splitter says, okay, fine, give me all 8, but only bit 0 is coming out from the side what we call the split end. Are we doing okay so far? So one conductor out of 8 is coming out of this particular splitter, which is, hey, Tech, isn't this what we really needed? And the answer is, yep, exactly. This is exactly what we needed. So now we just have to reposition things a little bit so that it looks nicer. And since we need 3 instances of this, I'm just going to work with duplicates. So we have 1 duplicate to connect from here to here. And then we have another duplicate to connect from here to here. And then we need this one, the third one, to go to here. Except you go like, but Tech, isn't the direction a little bit problematic? Because the Cat5 in this case is on the right-hand side, the split end is supposed to be on the other side. Now, if you're one of those people who go like, I don't want to do some extra work just to make something look nicer, you can get away with it. Okay, this is what you can do. You can say, oh, the merge end is where the 8 wires are located. That will still go to the 8-bit thingy. And then the split end, which is the one single bit that we want to pay attention to, oh, we just kind of do something ugly like that. Gets the job done. Does it look good? No. Is there a better way to do this? Yes. But would I count this as a correct solution? Yes. All right. So now we have, an 8-bit input pins, 2 8-bit input pins, and 1 8-bit output pins, where only bit 0, which is the rightmost bit of the input, matters. And only the output pin is only pay attention to also bit 0 of the output pin. And you guys will go like, why are we wasting time to do this? Well, that's because when I'm testing your circuit, the test mechanism is a multi-bit input and multi-bit output thing. I also want to give you guys the exposure of the concept of a splitter because it's going to be useful throughout the entire semester. So just push that concept a little bit earlier. And then what if you just look at me and go like, Tech, the way you explain stuff sucks. Okay? Is there an alternative way to find out how a splitter works? Because I don't think I can handle the way you explain stuff. What do you think? Where do you think you can find an alternative explanation of how to make a splitter works?
YouTube.
YouTube is one, yep, but the library reference, exactly. I mean, with a good library reference, I don't even need to be here, right? I mean, you just go to library reference, and it pops up, this little box here, and then it has the same organization. In case you haven't noticed, the organization of the library reference is a mirror to the templates of components. So the positioning and everything is identical. So now you click on splitter, you go like, oh, okay, so I just have to read through all of this stuff here. Okay, so this is an alternate way of reading about how components work. Alrighty. And we are almost running out of time, even including the lab portion. And I know you guys are getting tired because people are yawning. So look at this circuit here and go like, what is the big deal? I mean, we spent 3 hours, close to, well, actually just about 2 hours, but we spent 2 hours to create this little circuit here, and it doesn't seem to do anything useful. Yeah, we flip the input and the output changes a little bit. What is the big deal? So for this portion, I'm just going to use the whiteboard because the notes has the truth table already. So, but I do want to kind of go over this at least superficially so that you guys know the direction of where this is headed. So if we call the top input pin X and we call the bottom input pin Y, doesn't really matter because it's symmetric. And then the output, I'll call it Z, okay? So out of experimentation and because of our understanding of the circuit and also how transistors work, we now say, oh yeah, we kind of know what this works, how this works out. 0, 0, has an output of 1. 0, 1 has an output of 1. 1, 0 has an output of 1. And then 0, 0 has an output of, oops. I said something right, but wrote it down wrong. It's a very special skill. There we go. So if both inputs are ones, then the output is a 0. You look at this and go like, it doesn't remind me of anything. It is not an AND, right? Because if it were an AND, then 1, 1 being a 1 would be the only row being a 1. It's not an OR, because if it were an OR, then 0, 1 would be a 1, good. But 0, 0 would be a 0, too. So you look at this and go like, but this doesn't match anything that we have learned. But if you think about the principle, okay, of how is this different from an AND? It's different from an AND, okay? That's the first thing we noticed. But how is it different? Yep.
Is this a negated AND?
It's just negated. Okay? If you looked at, okay, so keep this around, but think about what is X and Y, okay? Just X and Y. 0 and 0 is a 0. 0 and 1 is a 0. 1 and 0 is a 0. 1 and 1 is a 1. See how Z is the opposite of X and Y? So Z is known as X NAND Y. NAND because it is negated AND. And I know we are out of time, but I do need to finish this because this helps to connect to the next lecture. And I will do the lab component. I'll send you guys a notice, an announcement of how to do the lab. I'll give you guys until the start of the lecture on Wednesday to get the lab portion done. Okay, that's plenty of time because it's supposed to be done in about 30 minutes. Okay, so don't worry about how much time for the lab. What is the big deal of NAND? Well, as it turns out, this is the only operator you need. When you took CISP310, your professor said, well, here's AND, here's OR, and here's negation. Well, that turns out to be unnecessary. If you have NAND in a programming language, the other 3 logical operators can be made as, using NAND as a component, you can make the other 3. So NAND is kind of like an interesting thing because it can be the only logical operator underlying negation, conjunction, and disjunction. And why it is important in this class is because now we can say, if you need AND or not in a circuit, they can all translate to just a whole lot of this circuit here with 2 p-channel, p transistors and 2 AND transistors. The idea is it can be done. Okay, we now have a way to translate logical operators to configurations of transistors. We have the lowest level of constructs now. That is the significance of this discussion. The details you kind of have to read and do the lab and to kind of get a better understanding. But when you look at it from the forest perspective and not counting the pine needles, that is the significance. Now we have a way to implement logical operators that you are familiar with using transistors. Just lots and lots of them. Are we good? All right, so that's the end of the lecture. I will give you guys the link to the recorded lecture, like almost right away, and then open up the lab, so-called lab. It's now basically homework assignment. But because I went through the entire process in class demonstrating how to construct the circuit, that's exactly what you need to do to turn in. So I think most of you can just kind of do it, follow the instructions, and get it done. If not, come to my office hour, or request an office hour, and I will be able to kind of go through this with you individually. Are we good so far? All right. I'll see you guys on Wednesday. Unless you're also in my 4:40 class, then I'll see you at 3. Most people cannot handle more than 3 hours of my lectures. I know I cannot. If someone makes me watch my own videos for more than 3 hours, I think I'll just pass out.